In the previous slides, we examined processes involving the heating, cooling, compression, or expansion of substances. Now, let us examine qualitatively hidden work in processes such as chemical reactions. Chemical reactions can be characterized as endothermic or exothermic. Examples of endothermic reactions are the photosynthesis of sugars and the cracking of hydrocarbons, the process of breaking down large hydrocarbon molecules into smaller ones. Dissolution in water of salts such as ammonium nitrate or sodium chloride or potassium chlorate are also endothermic. Dissolution in water of gases, strong acids or strong bases, is generally exothermic. Combustion reactions with oxygen or with air are exothermic. On this slide, I have written the combustion reaction for glucose, tristearine, and urea at room temperature. Note that the complete combustion of organic molecules containing only carbon, hydrogen, and oxygen leads at room temperature to the formation of carbon dioxide gas and water liquid. The combustion reaction of nitrogen containing organic compounds, for example urea, produces molecular nitrogen as a gas in addition to carbon dioxide and water, unless the temperature is extremely high, in which case various nitrogen oxides may also form. Sulfur-containing compounds typically form sulfur dioxide gas in addition to carbon dioxide gas and water liquid. In this class, we will restrict ourselves to the combustion reactions or photosynthesis for most thermodynamic calculations. So I expect you to be able to write such reaction equations in balanced form. In the following slides, we will consider three different ways of carrying out the combustion of urea. Our system consists in all cases of 1 mole of urea and 1.5 moles of oxygen gas at room temperature in a cylinder sealed from the surroundings by a piston. The cylinder piston assembly being placed in a large water bath kept at constant temperature. In the first example, case A, the piston can move freely and the walls of the cylinder are diathermic. Combustion of 1 mole of urea consumes 1.5 moles of oxygen and produces 2 moles of gas, that is 1 mole of carbon dioxide and 1 mole of nitrogen. Hence, the reaction results in a net increase in the number of moles of gas. Because the piston can move freely during the reaction, the pressure inside the reaction chamber will remain equal to the external pressure, and the increase in the number of moles of gas will result in an expansion of the system. The system is pushing its boundaries into the surroundings, opposed by the external pressure. So the system is doing work on the surrounding. That is, the work done by the reaction is negative. The combustion reaction is exothermic, and the cylinder walls are diathermic. So the heat generated by the chemical reaction flows from the system into the surroundings. That is, the heat Q is negative. The temperature of the system remains constant because the heat of reaction is dissipated in a very large water bath. From these observations, we conclude that the decrease in chemical energy of the system is associated with the production of work and the release of heat by the system. The chemical reaction takes place under isobaric and isothermal conditions. In the second example, case B, the piston is locked, so the volume of the system cannot increase as a result of the reaction. The walls of the cylinder are diathermic, so the heat of reaction flows in the surroundings and is dissipated in a large water bath. So the reaction occurs at constant temperature and constant volume. Since the number of moles of gas increase during the reaction, so does the gas pressure. Remember that as a first approximation, we can write pressure equals number of moles of gas times R times the absolute temperature divided by the volume. In this case, there is no change in volume, so there is no work of expansion, and all the chemical energy is transformed into heat. We can conclude, therefore, that when the reaction is carried out following the scenario B, it generates more heat than when it is carried out following scenario A. In the third example, case C, the piston can move freely during the reaction and the cylinder walls are adiabatic. The fact that the piston is able to move freely implies that the volume of the system can increase in proportion to the increase in the number of moles of gas. Hence, work will be done by the system. The fact that the cylinder walls are adiabatic implies that the heat of reaction cannot escape the system. Hence, the heat of reaction must give rise to an increase in the temperature of the system. The increase in the temperature of the system results in a further increase in the volume of the system, hence leads to a larger work done by the system in case C than in case A. In case C, the chemical energy is completely transformed into work. So, carrying out a chemical reaction using different paths or conditions leads to different amounts of work and heat exchanged between the system and the surroundings. We said that heat and work are path functions. More will be said about the difference between heat, work, and energy in the next chapter, when we look at these processes quantitatively.